हेलो। हेलो।
हॅलो सर.
हा, येत आहे ऐकू आता?
हो सर.
ओके ओके, ठीक आहे. मग मी आता फक्त माझं स्क्रीन शेअर करतो आणि प्रेझेंटेशन सेट करायला आपण बघूया मग.
येस येस सर.
ओके.
हो. मला पण व्हिडिओ माझे बरोबर. व्हिडिओ ऑन आहे आपला.
सर आवाज नहीं आ रही है.
हाँ हॅलो सर.
हॅलो.
हाँ सर.
हा, दिसतंय प्रेझेंटेशनचं हे पहिली स्लाइड?
हो सर.
ओके. आणि आवाजही व्यवस्थित आहे?
अगदी. येस.
ओके ओके, गुड. सो ऑल सेट. 3ला चालू करायचं ना, कारण तुम्ही बहुतेक स्ट्रीमिंग 3ला
हो
हे
हो
करणार असाल.
हो सर. हो हो 3ला सुरू करतो मी. बरोबर.
ओके ओके.
येस.
आणि अबाउट 40 मिनिट्स आपण
ठीक आहे ना सर. ठीक आहे सर. मी बोलतो तुमच्याशी. म्यूट कर. सरांना पण म्यूट करतो ना आपल्याला.
सर आवाज नहीं आ रही है.
तर परत ते
मैम आवाज नहीं आ रही है.
Dear participants, we are about to start our session very soon. Please be with us. Kindly mute yourself and keep your cameras off. Thank you.
మళ్ళా రుక్మిణి వాళ్ళ ఫ్రెండ్ తో అంటుంది ఈరోజు పంపు కొట్టింది.
Hello.
Yes, sir, we can hear you.
Yes. Okay. So finally, so just need to get the presentation, I think,
Yes,
on
sir.
the screen.
Yes, sir.
So let me give it 2 more minutes.
Yes, sir. Sure. Dear participants, we are about to start your today's session. Please be with us. Thank you. Hello, Kole sir.
Yes, Rajeshri madam.
Yes, yes, sir. Okay.
We can start now, no?
Yes, yes.
कोल्हे सर मला एनेबल करावं लागेल स्क्रीन शेअरिंग साठी.
Yes, sir.
Yes, sir, we are doing.
Host केलाय sir. Already
नाही आहे.
केलाय
No,
sir.
no, we are doing it.
Just
We are doing it.
अच्छा, कारण मला मेसेज येतोय होस्ट डिसेबल्ड पार्टिसिपंट म्हणून.
Yes, yes,
Okay,
yes, we are
okay.
doing it.
Done, no? Okay. Sir. Now it is there. We have made you co-host.
ओके.
Yes, yes. Yeah.
Hello, Kole sir.
Yes.
Can we start now?
Yeah.
Yes, yes.
Okay.
So should I start?
No, just a minute, sir.
Okay,
Just
fine.
a minute.
Yeah.
Welcome all. Dear participants, we are fortunate enough to have the eminent personality, Professor Parag Gopte from the Prime Institute in our chemical engineering domain, that is Institute, with us as a resource person for today's session in this faculty development program. It gives me immense pleasure to introduce Professor Parag Gopte on this occasion of faculty development program. Professor Gopte completed BChem, MChem, and PhD from Institute of Chemical Technology, ICT, Mumbai, India, and is currently working as professor in chemical engineering at ICT. The main research interests of Professor Gopte include cavitation phenomena, wastewater treatment, design of multi-phase reactors, separation processes, and process intensification. Professor Gopte has published over 300 research papers in international journals and has also written 25 chapters in books. Professor Gopte is a well-cited researcher with over 14,600 citations and an H index of 64 as per Scopus, over 19,600 citations as per Google Scholar. Professor Gopte has given over 90 invited talks or seminars globally and also participated in 20 international conferences. Professor Gopte has received many honors, including all the young scientist or engineer honors of all major institutions or academies in India and also of IChemE, Institution of Chemical Engineers, and SCEJ, the Society of Chemical Engineers, Japan. Professor Gopte is also fellow of IChemE UK and INAE, that is Indian National Academy of Engineering. Professor Gopte is also consultant to few industrial organizations in the area of process intensification, process improvement, and wastewater treatment. Professor Gopte has contributed extensively to the development of the profession by virtue of organization of refresher courses or seminars for participants from academic institutions or industries, and also competitions for student community. Professor Gopte has been involved in international collaborations with groups in Germany, France, Hungary, Portugal, Brazil, and Ukraine. Professor Gopte was also a visiting associate professor at the Purdue University, USA in 2010. Professor Gopte will speak today on hydrodynamic cavitation, a novel approach for water and wastewater treatment. I now request sir to deliver the talk. Please, sir.
Okay, thank you, Dr. Kolle, for a bit lengthy introduction. I had sent it to you as I thought you were like printing some online brochure or something. For the formal introduction, it would have been short. But anyway, so thanks very much. And I would like to thank MGM for inviting me to deliver this particular lecture as a resource person. So thanks very much. What I'll do is I'll just turn off the video so that it will prevent some bandwidth for me. And then,
Okay.
of course, the lecture we will continue. So today I'm going to talk on hydrodynamic cavitation, a novel approach for water and wastewater treatment. So when we look at cavitation, it is mostly taken in a negative manner, because what we have heard most of the time is to avoid cavitation, and especially in the area of fluid dynamics, because cavitation in pumps, as all of you would understand, that it's a detrimental phenomena, leads to erosion and needs to be avoided. But hydrodynamic cavitation, if you tailor it and focus it towards the application without really affecting the reactor, it can do some wonders. Yeah, Kolle sir, any problem?
Sir, can we make the screen a full screen?
Screen is already full screen.
Sir,
Okay.
sir, we
Okay.
mean it, sir, Gokte sir.
Huh.
Can we go to the slideshow mode?
Yeah, it is slideshow mode only, as seen
Okay.
to me at least.
We are seeing as in Word file mode.
Word file,
Yes.
like this.
This is PowerPoint now. Just
Yes.
make it a slideshow, sir. Thank
Yeah.
you, sir. Yeah, it
It's
is.
there now?
Yes, sir. Yes, sir.
Yes,
Okay.
sir. Thank
Okay,
you.
fine.
Thank you. Thank you.
Right. So let's continue. Yeah. So if you look at nature, that is also utilizing cavitation. And this is a very classical old movie, but still it makes a very interesting depiction. This is a snapping shrimp, which was captured in University of Twente, Netherlands. And they are showing that even the snapping shrimp is generating a cavity which is traveling a certain distance, and then it is collapsing. So the things would be very clear in the top view. Here you are clearly seeing that something is released, it travels a certain distance and collapses. So if you look at it in engineering aspect, what you can do is try to map pressure at different locations. So point number one here, point number one, which is release of the cavity. Point two is traveling. And then at point three, where the collapse was seen, you must have seen in the movie that everything is disappearing. And there, if you make the pressure mapping, you are clearly seeing that there is a large increase in the pressure pulse. So all that it says that at the moment of cavity collapse, you are getting a significant increase in the pressure pulse. What we need to do as design engineer or as engineer, we need to replicate nature, and the aim of hydrodynamic cavitation reactors will be to replicate this phenomena. But I don't want like one snapping shrimp to work in my reactor, because that will be too localized phenomena. So what I need is I need to achieve it at multiple locations simultaneously in the reactor. As I have just said, that the earlier investigations dealing with hydrodynamic cavitation were mainly directed towards avoiding it. And people might remember cavitation even in World War days, because the large military ships, warships, were having a peculiar problem of erosion of the propeller blades. Remember, propellers on warships are going to rotate at a significantly higher speed. So that also is going to generate cavitation. And because the cavities were collapsing near the blades, it was also leading to erosion. Concentrated efforts by few research groups worldwide have led now to harnessing the positive effects for hydrodynamic cavitation. Let's see how we are going to generate cavitation. So imagine a pipe flow and you have an orifice right at the center. What is going to happen is, because of your Bernoulli's principle, you know that once the liquid is passing through the constriction, the velocity is going to go up because area is significantly reducing. So once the velocity increases, your pressure is going to go down significantly. And if it falls below the vapor pressure, you will generate cavity. These generated cavities, of course, are going to travel downstream on the orifice, and then it's going to undergo pressure fluctuations. People know that there will be eddies which are going to be generated, and this will drive the different stages of cavitation. So definitely you are going to get significant effects downstream of the orifice, and this relates to whatever cavitation effects you are going to generate. Now, orifice plate is only one example of the cavitation device. You can also have throttling valve. You can have venturi, which can be either a circular or a slit type venturi, which we describe as non-circular. And it can be also a high-speed homogenizer, which is going to have again impellers or stators and rotors, which are going to rotate at significantly higher speeds. And in orifice, you can also have either a single hole orifice, or you can have multiple orifice plates which can be inserted as cavitation device. So what is going to happen? You will have cavity being generated in the system, and then it's going to collapse. So there are three different zones which happen in cavitation effect. One is you are going to generate nuclei, which is going to grow to a certain size, and then it's going to collapse. So on the screen, you can see that there is some sort of time on x-axis, radius on y-axis, and you can clearly see that there are two profiles which are going to be possible. One, we call it as a steady cavitation. Second, we call it as a transient cavitation. The difference is clearly that in steady cavitation, you are going to have multiple oscillations, and the pressure field which is going to be generated is going to be lower or of less intensity. Whereas in the case of transient cavitation, you are going to get a significant increase in the cavity growth, and then there is a sudden collapse which is going to give you intense cavitation. So people have again visualized this, and these are again some videos which are for your own like understanding. You can clearly see that this is just a stable type of cavitation, whereas this is a transient cavitation, and there is a large liquid which is being circulated around the site of collapse. So the effects are going to be much higher in the case of transient cavitation. Now, if I want to talk about process intensification, I would look at the key aspects for process intensification. One is you are going to have localized intense pressure and temperature conditions, which are equivalent to say hotspots. Imagine like local pressures and temperatures to the tune of few thousand of degrees Celsius and few hundreds or sometimes even thousand atmosphere pressures. Now, it's not going to be over the entire reactor zone, but it's going to be over the local microscopic scale. So your overall reactor, nothing is going to happen, but whatever liquid is going to expose to these particular conditions, you are going to get significant effects. And one of the effects would be generation of highly reactive free radicals. So in addition, you are clearly saying that because the things are happening locally, there is also a concentrated energy dissipation at the location of transformation. In addition, there is also generation of high intensity turbulence, increased transport coefficient, and this, if you combine everything, you can get order of magnitude reduction in the energy requirement for physical and chemical transformation. If you look at the highly reactive free radicals and local hotspots, these are going to intensify your chemical processing applications, say reactions, say wastewater treatment, whereas high intensity turbulence, increased transport coefficients are going to be significantly useful for the reactions which are going to be limited by mass transfer, or the applications which solely depend on physical effects. So what also I want to highlight here is, depending on the application, you can also tailor either the chemical effects to be maximized or the physical effects to be maximized. Because what is going to happen is the energy requirement for generating cavitation and concentrating on the chemical or physical effects are going to be requiring different energy requirements. So that you need to take care. But as an overall objective, you can definitely achieve an order of magnitude reduction in the energy requirement for physical and chemical transformations. Remember, we are all engineers, so definitely we need to control the phenomena and use the effects in a positive way. That's going to be bottom line, because the initial research was focused on avoiding it. So it has some power which can give you negative results. I need to use only it in a positive manner. So I'm just going to give an outline about the talk. So I'm going to talk about cavitation concepts we have already seen. So some discussion will be on the possible reactor designs. It's going to be quite simple. We will see some of the case studies, say from water disinfection or effluent treatment, and we will also see combined processes, and then finally conclude the talk. So in reactors, you can either have a high speed or high pressure homogenizer. So all the loops typically are going to be similar. So you'll have a feed tank where you are going to have a pump which is used for recirculation of the fluid. Then you are going to have either a high speed or a high pressure homogenizer or a cavitation device in the recirculation mode, and the liquid is going to be recirculated back into the feed tank. So this is the general outline of the reactor configuration. And this particular region, the first stage, second stage homogenizer, can be variable. So either you can have a homogenizer, a high speed device, or a high pressure device, or you have a orifice, or you have a venturi. This can be, or you combine it with a ultrasonic flow cell. So all variations can indeed be possible. So this is the orifice plate setup, which is there in the Institute of Chemical Technology. And some of you already worked. Rajeshri definitely, Aarti also must have worked. Even if I'm not, Dr. Kolle also might have worked during his PhD, though it was with Professor Rathod. But so this is the setup, yeah. And this is the hydrodynamic cavitation tank. So you again have a centrifugal pump which you are going to recirculate the liquid back. There is a provision for cooling water, which is CW in and CW out of the reactor. So this will allow you to maintain the temperature of your fluid inside the tank. There is also a bypass line which will allow you to control the flow which is going to go through the cavitating device. So I can only operate this in a recirculation mode without really going through the cavitation device, or I can have maximum flow through the cavitation device depending again on the application. So this loop just gives you an idea in terms of how you can control the operation. Remember, this cavitation device, you can have different orifice plates, like single hole orifice or a multiple hole orifice. So I would have some depiction of different cavitation chambers. So this is circular venturi, slit venturi, orifice plate, only a single hole, say of 2 mm diameter. Now you must be wondering, why do you require such kind of different devices? The answer is definitely each application would require a critical cavitational intensity for having maximum benefits. And this is going to depend on what cavitation chamber you are going to use. So a single hole orifice would give you much higher intensity. Venturi would give you medium type intensity, but that might be suitable for a specific application, and then it's going to be easy. And remember, again, if you remember your experiments in fluid flow regarding the orifice meter and venturi meter, definitely you will understand that there is a significant pressure loss in the case of orifice and much lower pressure drop in the case of venturi. And this also means that your energy requirement in these two types of devices is going to be different. So once you are designing or applying any particular system, you need to look at the operation using different angles. It's not only that you need to look at what will happen when you are replacing orifice plate with venturi to my cavitational intensity, but you should also look at the energy requirement. So optimization is going to be extremely important. So again, there is some depiction in terms of what type of different holes you can use on the plates. And remember, these holes are only circular, but and the circular meaning it's going to be very easy to drill a circular hole on the plate. But if you can do, you can also get triangular or a square type holes, because that is going to change your perimeter to the cross-sectional area parameters, and this is going to affect your cavitational intensity. So definitely that's going to be very important. This is another kind of setup, a hydrodynamic cavitation setup with stator and rotor type of assembly. The loop is very similar. You will have a feed tank, a pump, a cavitating device, and you are going back into the same tank. Here, there is an additional provision of heat exchanger. So because you are having a heat exchanger here, definitely you can change the operating temperature and maybe operate under heating conditions as well. In the earlier setups, you just had a provision of cooling water, but no heater was being incorporated. Here, that possibility is there. So this is a typical stator rotor type assembly, and you can see clearly again this rotating cylinder is having multiple holes, which allows you to have a fluid interaction. This schematically shows how you are going to get interactions and then the cavitation phenomena. So again, it's kind of a flow loop. Now, if you want to understand cavitation in depth, you need to also look at the theoretical aspects, because you need to look at the hydrodynamic cavitation modeling. Now, people don't really want to spend time on modeling, rather spend a lot of intellectual energy on modeling. As compared to that, doing experiments is going to be simpler. But definitely, if you are keen on modeling, you can definitely understand the phenomena fundamentally or in depth. So I'm going to just present some slides even on modeling. That should not afraid some of you, but so I'm going to keep it simple, not going to talk about detailed solutions. Let's try to understand this in simple words. So when I look at bubble dynamics approach, there are two common approaches which are used. One is a simple single cavity approach, and second is a bit complicated cluster approach. And a simile of this single cavity approach and cluster approach lies in your sedimentation, which is a simple chemical engineering operation. And you must have heard about free settling and hindered settling. So in free settling, you are going to have one particle falling in a pool of liquid. In hindered settling, there are just too many particles which are going to fall down in a small pool of liquid. So each particle is affecting the motion of other particle. Same thing here in single cavity. You have very less number of cavities being generated in an infinite pool. So the collapse or dynamics of one cavity is not affecting the other cavity. Whereas the cluster approach, there are too many cavities which are going to be generated, which is definitely required when you are talking about a large scale application. So that way you need to look at the interactions between the cavities, and this will give you a more realistic picture. So if we can optimize the cavitation reactors, I can arrive at what is the best geometry and then try to construct that particular geometry for my desired application. Remember, theoretical simulations, though it appears complicated, are the easier way of optimizing the reactor, because you don't have to construct too many reactor configurations and then try to perform too many experiments. You can just construct simple flow loops in your CFD or similar softwares, Fluent, and then get the prediction of cavitational intensity. So if you can sort of approach it in a fundamental manner, things always are better. So let's see now some theoretical understanding. So there is a cavitation number which allows you to predict whether cavitation is going to be possible. So it's a simple ratio of pressure drop per unit kinetic energy. And ideally, when cavitation number is less than 1, cavitation happens. So it can happen sometimes when cavitation number is greater than 1, particularly if you're having dissolved gases or impurities in the system. But for maximum benefits, one should maintain CV less than 1. Typical range would be around 0.2 to 0.4 or in that range. So that will give you maximum benefits. So simple solution to bubble dynamics equations, you will have again flow through the orifice. You know that there will be a vena contracta which will be generated. Then there will be pressure recovery without turbulence, pressure recovery with turbulence. This is very similar to your stable cavitation and transient cavitation. You have different equations, so I'm not going to go into details. I already shared the presentation. So, but I'm just highlighting the approach to be followed. So with turbulence, you have the sinusoidal frequency of turbulence, which is considering your turbulent velocity. And this is the L is the Prandtl length scale of eddy, and which is based on your orifice diameter and pipe diameter. So you basically, based on the geometry, calculate length scale, calculate frequency of turbulence, and then use it to calculate the turbulent velocity, and then use it in the actual pressure drop equations, which will be used in your bubble dynamics equation. So this is just an idea about what kind of differential equations are used. So this is dr by dt, which is the bubble wall velocity, bubble wall acceleration. And then this P infinity is going to be dependent on the pressure drop, the earlier equation which we saw. So this is another equation which considers the compressibility of medium. So we are not going to solve this, so don't worry on that. But yes, you can solve it, generate what are called as the radius time profiles. And a steady cavitation again is similar to what we have seen earlier. There are a lot of fluctuations, and in transient cavitation, you are going to just get a maximum and then significant collapse. And the idea of showing the conditions here is that depending on the conditions, you can generate either the steady cavitation or the transient cavitation. Typical bubble dynamic simulation will give you instantaneous values of all these parameters and the liquid physicochemical properties, which can be used for the quantification of collapse pressure pulse and the temperature conditions, which can be then used to relate your kinetic condition. So let's look at some of the optimum recommendations for the liquid phase physicochemical properties. So liquid vapor pressure, viscosity, surface tension are the key parameters which are responsible for controlling the intensity of cavitation. Viscosity in particular, if the viscosity is high, then you might have no cavitation in the system. So the favorable conditions are liquids with low vapor pressure, low viscosity, low surface tension, and the most available fluid satisfying these requirements is water. So definitely there would be many applications of cavitation because water is going to be easily available. In addition, the liquid temperature and presence of dissolved gas solubility or the polytropic constant is also affecting the cavitation, and some of the favorable conditions have been given. We have already seen that cavitation number should be less than 1, but there are some recommendations also given in terms of the inlet pressure, So if you operate at higher inlet pressure, definitely there will be an intense cavitation. The onset of supercavitation needs to be avoided. So I don't want my CV to go below 0.1, and I can use plates with smaller size of the orifice holes and large in number to get maximum benefits of the shear layer. So that is additional recommendation on the geometry aspect. Comparing orifice as against venturi, so intense flow or intense requirement of cavitational intensity will mean that orifice flow is better. But for milder processes requiring pressure typically between 10 to 15 to 20 bar, and for physical effects, even a venturi configuration will be more suitable and energy efficient, because I had already said that in a venturi you are going to get lower pressure drop, which means your energy requirement are going to be lower. Higher cavitational intensity will be required, so mostly you need to use higher discharge pressures. For milder reactions, even lower discharge pressures are sufficient. So if I'm having venturi and I want to increase the cavitational intensity, I can just reduce the length of venturi or reduce the venturi throat to pipe diameter ratio. In terms of orifice, I can increase the pipe size downstream of the orifice, which offers a faster pressure recovery, or I can increase the number of holes, which also can, sorry, and I can also decrease the size of the hole. So these are just some of the recommendations which can be used to maximize the cavitational intensity and hence the process intensification benefits which you can get for the reactions. Right. So after looking into the theoretical concepts, we are going to look into some comparison with acoustic cavitation. So I'm going to highlight some of the case studies, which again has been based on the work done at ICT. Comparing acoustic cavitation. Now, why this is important? Because traditionally, over last like 50, 60 years, acoustic cavitation, which is based on using ultrasound, has been dominantly used. So whenever you are kind of suggesting alternative, so hydrodynamic cavitation is an alternative. Whenever you are suggesting, you need to compare it with the well-established technique. So let's compare some results with acoustic cavitation. So degradation of paranitrophenol. So the reaction volume is about 7 liters, energy dissipation rate 1000 watt. So we use a parameter which is called cavitational yield so as to quantify the effects per unit energy supplied. So in the case of acoustic cavitation, it's usually less. So here it is 2.25 into 10 raised to minus 5. The relative numbers are important. So hydrodynamic cavitation gives you 3 times more effects per unit same energy supplied. If you can compare it with the degradation of rhodamine B, now rhodamine B is a pink colored dye, effluent. Dyes, you know, have significant problems because color is the most visible form of pollution. So you need to treat all your dyes, and these dyes, most are biorefractory. So your conventional biological oxidation may not work in this case. And then you need to look at some alternative treatment schemes. So hydrodynamic cavitation, typically this is plate 1, plate 2, gives you much beneficial effects as compared to the ACE horn or the horns, basically, which are ultrasonic reactors. And in ultrasonic reactors, if you really want to compare, some multiple frequency units are more giving energy efficiency as compared to the horn type. Now, again, the lecture is not about ultrasound reactors. I'm not going to go into details of that. But in essence, hydrodynamic cavitation is more suitable as compared to your ultrasonic based reactors. So if in a nutshell, we want to compare scale of operation, definitely hydrodynamic cavitation is easier. Acoustic is more suitable for smaller scale or medium scale. Energy efficiency is high. Acoustic cavitation, you get lower energy efficiency. Flow, there is already a flow loop. The only disadvantage is sometimes you get low cavitational intensity in the case of hydrodynamic cavitation, whereas acoustic cavitation is significantly higher. So that need to be taken care of depending on the application. So if it is low, we need to look at how I can further synergize the effects. And one of the approaches which we are going to see here is combine it with chemical oxidants. So let's see some of the environmental applications. So water disinfection and treatment. Typically, bore well also has a lot of microorganisms. So if I want to treat it, can cavitation can be used. So this is very initial studies which was done, and definitely there was disinfection in terms of the total coliform skill depending on the operating conditions, and treatment type of 60 minutes you are able to achieve about 80% killing. So definitely it has disinfection capacity. It had also shown good application in seawater disinfection, and the kind of commercial application for seawater disinfection would be what is described as a ballast water treatment. Whereas for borewell water disinfection, in borewells, if you can insert a hydrodynamic cavitation device, your cleaning is going to happening right at the kind of the when the liquid is coming out from the earth's crust. So definitely that treatment is much more efficient. You don't have to post-treat it once you get water. In the case of seawater disinfection, as I said, the application would be in ballast water. There are some more case studies like degradation of reactive red 120 dye, and this is another dye which is used again. As I said, dye is the most visible form of pollution. So we have studied with a lot of dyes. So one of the case studies is based on reactive red dye. So here we are going to look into the combination approach. So the first combination which was thought about was using steam. So steam again is a gas when you are inserting it into the liquid, and with steam there was some difference because the blue line shows it without steam. So it's a slow type degradation. With steam you are going to get a significant increase. So if you look at 30 minutes treatment as a comparison, it's about 12 and about 16. So there are some increase which is happening with steam, but more importantly, we are going to look into the addition of hydrogen peroxide. So about 10-20% degradation is happening without H2O2, only in the presence of hydrodynamic cavitation. With hydrogen peroxide, there is a significant increase and you are reaching to almost 90%. Now, hydrogen peroxide, remember, is going to give you hydroxyl radicals when you are combining it with hydrodynamic cavitation, and these hydroxyl radicals will give you much higher treatment efficiencies. So that is the main governing principle here. Right. One of the applications, we have been exploring this for so many years now, and one of the applications which we thought about was, can we enhance the biodegradability? Now, if you look at industries, most of the industries are going to use biological oxidation, and definitely hydrodynamic cavitation, if it is used as a supplementary, then the acceptability is going to be higher. Remember, whenever you are kind of putting forward a solution to any industry, usually industry will want an add-on solution. They don't want any replacement type solution. So because the capital cost is going to be minimal. So if we can say that hydrodynamic cavitation is going to enhance the biodegradability, so what it's going to mean is it's going to enhance your efficacy of existing biological oxidation. Definitely that's going to be much more recommended and acceptable. So a typical range of biological index or biodegradability index is 0.3 to 0.5. So we started with a kind of refractory effluent having a biodegradability index of 0.1. After treatment, you are reaching the magic figure of around 0.35. So within the definite range. So that is an advantage. You can also use cavitation with Fenton. The mechanism for synergism will be additional oxidation based on formation of complexes, enhancement in hydroxyl radicals. And here again, some of the rate constants are given for imidazole degradation. And clearly you can see that the only hydrodynamic cavitation is giving you much lower few ones. But if you are combining it, it increases to about 36, 40, and then in the presence of fenton, about 244 times. So definitely there is a significant increase in the extent of treatment. You can also combine it with photofenton and then get much better results. So finally you can reach 100% degradation of imidazole. Now the idea here is your combined treatment schemes are working better, but we need to also look at whether all combinations are useful. See, because if you combine here, Hc plus penton is giving you 98% degradation. Hc plus photofenton is giving you 100, so only about 2% increase, but you are putting in additional energy in the form of photo, which means UV light. If it is on the basis of solar, then there is not much of problem, but UV is going to be significantly energy intensive. So I need to look at the benefits and then only decide on which combination I would want to work. This is another like combination of hydrodynamic cavitation with advanced penton. So you have a orifice holder, which is this part is your hydrodynamic cavitation. This part is for advanced penton, which is typically iron pieces combined with hydrogen peroxide, which is while recirculating, you will have hydrogen peroxide added in the feed tank, and this can give you much higher treatment efficiency. And this again was tried out for complex effluent, and you are reaching about 40%, 60% reduction. The residual value was about 0.4, and the treatment time can be optimized as 90 minutes. Now remember, we have already said that this is not going to be a replacement technique. So it's going to be an add-on. So if I can add on, treat it for say 90 minutes, bring it down to about 0.4, after which your biological oxidation is going to be easier, definitely this is important. So let's talk about one case study which we have been working with a US-based company, Ecosphere Technologies. Now this is a combined reactor, ozonics, based on combined operation of acoustic cavitation, hydrodynamic cavitation, electrochemistry, and ozone. Key advantages of this particular hybrid combination is you will require lower dosage of ozone, which will definitely mean that you are dealing with lower costs of treatment. You will have application for a wide range of effluent because you are generating number of oxidants in the system. Cavitation, when you are combining with ozone, you will have mechanism in terms of increased mass transfer due to acoustic streaming, the liquid circulation which is generated by ultrasound. You will have production of enhanced free radicals, and you will have a combination of acoustic and hydrodynamic cavitation, which also gives you enhanced intensity of cavitational collapse. Ultrasound, there is also a component of electrochemical oxidation or electrochemistry. Again, electrochemistry is limited by mass transfer. So you will have increased mass transfer due to acoustic streaming, which will give you better effect. And you will also have production of enhanced free radicals due to the combined action of electrochemistry and cavitating conditions. This is the actual picture of ozonics reactor. So this is a schematic representation just to give you zones, which one is hydrodynamic cavitation. So this is based on static mixers. Two is the ozone injection zone. So ozone is going to be introduced here. Three are the flow cells or the ultrasonic transducers, which are on this particular pipe. And then you have four, which is electrochemical oxidation. The beauty of this, it is mounted on a self-contained trailer, mobile trailer. So you must have seen long containers going from one place to other. So you have an entire reactor which is mounted on this particular mobile trailer, and this gives you on-site treatment. Now the main application of this is oil and gas explorations. So in the case of oil and gas explorations, each oil and gas well will have a limited utility. So I can't have a capital investment there, and because once the oil and gas well dries out, my capital investment just vanishes. So I don't want a permanent installation there. So you can get this particular mobile trailer there, treat your water which is going to be used, recirculated, and definitely that's going to be suitable. So just to give you some science behind the applications, you are generating too many radicals. So cavitation, when I'm combining ozone with cavitation, I'm having electrochemistry. So again, hydroxyl radicals are generated. And depending on the system, because you are also treating your seawater or brackish water or your water which is going to come out from Earth's crust, so you will also have some chlorine present, and so you will have oxidizing agents based on chlorine as well. So definitely that is again an advantage. Some theoretical simulations were also done to understand the cavitational activity distribution, what levels of turbulence are being generated, how I can integrate it with chemical reactions, because it is important to predict the radical formation, and finally arrive at optimum design and operating condition. So some theoretical simulations were done based on the basic equation of sound pressure field, which can be solved using CFD COMSOL. Again, I'm not going to go into details of this, but I can integrate it with different radical reactions that are likely to occur and then predict my radical formation in the system. So some results from the theoretical simulations: cavitational activity distribution more or less is uniform throughout the device. So you can see some of these small circles, brown colored circles. These are location of transducers. So there is some high intensity at these transducers, but the overall picture also is showing you some cavitational activity. If you look at the velocity distribution, definitely there is a lot of velocity interactions, so turbulence is generated. And so this was just to confirm what levels of turbulence and cavitational intensity is occurring. The potential application sectors of these particular reactors. So it can be used for industrial wastewater treatment, pharmaceutical industries, pesticides, herbicides, insecticides. A lot of research work also has been done based on all these model compounds at ICT. It can be also used in distillery wastewater treatment. It can be also used in wood finishing industry, because a lot of alcohols are used and this cannot be discharged into effluent. So that can be treated. You can also use it for microbial disinfection, water treatment. So I can just look at a community groundwater supply. Definitely I can install hydrodynamic cavitation devices and then get a treated water. It can be also used in food processing industry as a replacement to thermal pasteurization. So thermal pasteurization, you know, your fruit juices are usually amenable to microbial contamination. So I can use thermal pasteurization, but the problem is that your nutrient quality can go down. So if I can use hydrodynamic cavitation, of course, a good design will be required, and it can serve as a replacement to thermal pasteurization, definitely maintaining the quality of fruit juices. So in ICT, we have done some experiments with ultrasound-based reactors, but recently some food department people are also working on hydrodynamic cavitation. So that definitely is a possibility. Ballast water treatment is a major problem in shipping industry. You know, a lot of oceans will always have a specific microbial population, and I don't really want to disturb it. What it also means, the water which is taken by the ships at a particular port cannot be just discharged at another port without any treatment, because whatever microorganisms are present, if they are just kind of discharged at another place in a different environment, definitely they would have problems. So that needs to be avoided. So onboard installations are going to be required again in circulating loops. Of course, one pass treatment is the key. So hydrodynamic cavitation does have a potential in ballast water treatment. Industrial cooling waters, definitely there is a possibility. So biofouling is a major problem. Now, biofouling is a common word. People will understand that, but even if you look at monsoon season, you will always find some green color algae or related sticky material depositing on the surfaces. So water in industrial cooling tower is continuously recirculated. So definitely, if you are having such kind of fouling, it will affect the heat transfer in the system. Chemical biocides are most commonly used, but these offer disadvantages. So I can have hydrodynamic cavitation again in the flow loop, because in industry, cooling water would always flow in a certain loop. It will go from a cooling tower to main plant, back to cooling tower. So in this, if I can use hydrodynamic cavitation, definitely there would be an application. It can also give you benefits of scale and corrosion inhibition. It can also have application in the area of municipal wastewater treatment, basically to enhance the biodegradability of the sludge, improve sludge digestion, and can also be integrated with biogas plants from municipal wastewater treatment sites, or even on farmland projects based on agricultural residue. So in your sustainable biomass conversion to biogas can be intensified based on hydrodynamic cavitation. So the success stories for ozonics reactor were mainly in oil and gas exploration, over 1200 hydraulic fracturing operations, and you have proven applicability at commercial scale. So I think we are approaching, yes, 4 o'clock, and there are just about 2-3 slides remaining. So this is a good picture showing you the same ozonics reactor, photos of influent and the treated effluent. So definitely on the left side of the screen, you have a black colored influent, but at the outlet, you have a milky kind of suspension, but definitely I'm not going to drink it. I'm going to just recycle it back in the plant, and that is suitable. So there is a clear difference in the treated water. Let's look at how I can, just as a passing remark, how I can intensify my cavitational activity. So in the earlier loops, I have a feed tank, which is a reactor reservoir here. I have a centrifugal pump, pressure indicator, which is going back. I had only one orifice plate in all the earlier loops. But what happens if I have 1, 2, 3, 4, like a cavitation zone? Definitely I'm going to have intense cavitation being generated here. Of course, this is also going to give me a lot of pressure drop because I'm having so many obstructions for the flow. So definitely there would be a problem. But yes, I am going to get an intense cavitation happening, and the application can be improved based on that. So this is one of the ways which I can improve. Second way is I can just have a combination of orifice plate, which is here, with ultrasonic flow cell, and then again the recirculation continues. What it's done here is you're generating cavitation using hydrodynamic mode, and the collapse happens in the flow cell. So definitely that is an advantage, and then the recirculation can continue. Right, so we come to the last slide, and then I'll be happy to take some questions. So what we have seen here is there are already established guidelines for optimum parameters and reactor configurations, which reactor to choose, whether it should be a orifice, whether it should be a venturi. The efficacy of hydrodynamic cavitation reactors definitely is established as compared to the acoustic reactors. It definitely offers a good potential for industrial scale applications, especially for wastewater treatment, cooling towers, avoiding biofouling. Scale up is easier. You have vast amount of information already available, and the operating efficiency, more important, of the circulating pumps, which is the only energy dissipating device in the system, typically is always higher at large scale operation. So yes, and there are few depictions of use of hydrodynamic cavitation at actual commercial scale for wastewater treatment, industrial wastewater treatment, for cooling towers, for some specific applications in food industry, as I have just said, on food pasteurization. So there are good amount of applications in Italy based on food preservation. So they are also using a numbering up system meaning rather than having one big reactor to treat entire processed juice, they're using multiple units, and then the scale up uncertainty is avoided. So numbering up usually allows you to scale up the system without much of uncertainty. So that numbering up system they're using. Wastewater treatment, yes, there are also some commercial applications which are possible. Right. So this is what I wanted to say today, and it has been a good about 50 minutes talk. There were some problems initially, but after that, I think the presentation, there were absolutely no problems. So that's good.
Yes.
Of course, this doesn't allow the kind of enjoyment in a personal interaction, but the current situation, I think this is the best way to have some intellectual inputs based on some good speakers. I'm praising myself, but I hope you will also agree with me
Yes,
about
sir.
the thing. Yes.
Yes, sir.
So it
Yes.
was good talking to you. Then definitely we can have some questions at least, because I see the people, the participants, and it's good to have about 100. So it was like about 106, 105, just hovering around that. So it's a good kind of crowd in this
Yes, sir.
particular online webinar.
Yes.
So
yes.
good, Dr. Kole. And if you are having some
Yeah.
questions, we can have it. It was good interaction.
Yeah. Yes, sir. Thank you very much. Dr. Rajeshri, can you see whether some questions are over there in
Yes, sir.
chat box?
Yes, sir.
Please.
Mr. Guzer wants to ask, is it really necessary to have a bypass in hydrodynamic cavitation setup? What is at stake when there is no bypass?
Okay, so that's a good question, because the setups which we have in ICT definitely are always with bypass, whereas some of the setups which I showed based on collaboration with European countries, they didn't have any bypass in the system. So what is at stake is a good question. Your pump is at stake, because whenever you don't have any bypass, the entire pressure is going to fall on the pump. So if your pump can withstand that, your gaskets, your connecting rings, your seals can withstand that, you can get rid of bypass as well, right? But if your pump doesn't withstand, and that's the common problem with Indian pumps, you need to have a bypass, and then in the bypass operation as well, you don't completely close that particular bypass, because the moment you close bypass, it's going to be same as having no bypass in the system. So that's the kind of what is at stake answer. The difference it's going to make is in bypass, whenever you are having some liquid going through the bypass, it reduces the quantum of liquid which is being treated in per pass. When you don't have any bypass, entire material is going to go through the cavitating device, and then you get 100% treatment in that particular single pass. In bypass, whatever liquid goes through the bypass is not going to be effectively treated. So it's basically just
Hello.
yeah. Now it's unmute. So balance which you need to do between your capital savings and your actual operations. Okay.
The second question is from Reena Mhatre. At what pressure does cavitation occur?
So if I look at the inlet pressure to the orifice or any cavitating device, this will typically occur about 2 bar range. Again, it depends on what cavitation device which you are using. But what we have seen is for a simple multiple hole orifice, hydrodynamic cavitation starts at around 2 bar, reaches a maxima for the cavitational effects to about 5 bar, and then again it starts giving reduced effects because you reach what is called as a super cavitation. So between, I would say about 2 bar to 5 bar, you get best results, which is typically same in terms of 2 to 5 atmosphere. But this strongly depends on what is the cavitation device which you are using. whether you are using a bypass as well. So the geometry of the hydrodynamic cavitation device also would play a role in deciding the inlet pressure. And simple calculation based on cavitation number, because essentially it was pressure drop per unit kinetic energy. That calculation will tell you what pressure is required depending on what flow rate or velocity you are maintaining in the system. Right.
The next question is from Mr. Milin Surve. Can we use this technology for non-Newtonian fluids or heterogeneous catalyst reactors?
Non-Newtonian fluids, it will depend on what viscosity levels you are talking and what is the kind of non-Newtonian behavior you are looking at. If it is highly viscous, then definitely cavitation is going to be very much limited. So that will not give you much benefit. You will also require a lot of pump energy to circulate that particular non-Newtonian fluid. So it all depends on what viscosity levels and what is the non-Newtonian behavior you are looking at. For heterogeneous catalytic systems, you can definitely use it, but the only precaution which you need to take is about what is going to happen to the catalyst, because it's going to be a flow type system. So if your catalyst morphology is not strong, breakage of catalyst particles might occur. So that is a problem. So some catalysts can also remain, because if you look at the flow loop, it's all closed. Once you only have access to the feed tank, you do not have access really to any of the inside piping network and the centrifugal pump which you are going to use during the operation. Of course, when you take shutdown or cleaning is required, then you can have access to anything. But during the operation, you might face some amount of problems, because your loss of catalyst, your loss of catalyst morphology also can be an issue. So it again depends on what is the inherent strength of your heterogeneous catalyst.
There is another question from Mr. Ajit Kumar Gudekar. Hello, Parag sir. What is your experience with the industry for cavitation-based technologies? And he wants to thanks for refresher in cavitation.
Thanks, Ajit. So the problem with the industry is, especially the Indian industry, really speaking, they are not very keen in terms of having any capital investment for ETP related operation. So whenever you suggest them a solution, they will always ask in terms of what is the payback period or what is the return on investment. And once you give numbers, it might create some problem. There are some applications which are definitely tried out in industry in India as well, is for common effluent treatment plants, because common effluent treatment plants, most plants in India are facing problem because of the member industries, but there definitely some applications have been seen, and there are some case studies based on that as well. So it's slowly increasing, people are exploring it, but yes, it's much work needs to be done, especially in India. In US, that way it is significantly accepted, especially for the applications like what I presented, the case study based on the oil and gas water recycle, the ecosphere. They were doing very good business for 5-6 years. In cooling towers, you see number of companies which are supplying technologies. In Europe also, there are some applications, say for biogas, because municipal waste to biogas is and to electricity is a significant industry in Europe. So there you can use cavitation in general and it gives you good benefits. So in India, it's slowly coming up. In Europe and US, more or less, it is quite established now.
Okay.
Kole sir, can we have two more questions?
Rajashri, I have one question to
You
sir.
can-
Sir, good afternoon. It's
Yes,
Aarti here.
Yeah, good to hear your voice after a long time.
Yes,
So that also means, Aarti, you should call me at least once a month and try to
Sir.
keep in touch. Yeah, I know you are busy in MGM, but yes, good to listen to you. Yeah, you can ask question. Aarti,
Yes,
I think, has muted herself somehow. I don't know.
In the morning, I told Dr. Kole sir, that
Yeah.
I always fear to talk to sir. Sir,
There is no fear.
Yes,
really,
actually.
sir. Actually,
Yeah.
you mentioned that to intensify hydrodynamic cavitation, you
Correct.
have used that serial that cavitating equipment in series.
Yeah. So no, I haven't said we have used it because it's not
But
there in our kind of systems. But that is just a possibility. Yes.
okay, sir.
Yeah.
We also can go for parallel connection. That will, I think, better means that will be a better approach than going in series way.
Right. So
Means,
parallel. Yeah. So parallel is going to be better, but what you are going to get is same cavitational intensity in each parallel pipe.
huh.
Right? Because you have just kind of multiplied your hydrodynamic cavitation flow loops. So you
Yes,
are
sir.
going to get same intensity. So when you look at water, it's going to experience the same cavitational intensity, but at multiple locations. When you
Yes.
are using it in series, what is happening is the same water is going to experience much higher cavitational intensity. So
Okay.
that is the difference between a series and a parallel type system,
Okay, sir.
right? So if you require really high cavitational intensity, definitely series would be preferred. If you just want to multiply, then parallel also would be good.
Okay, sir. Thank you, sir.
Okay, thank
Sir,
you.
there is
Yeah.
one more question. As we are live on YouTube, there is a
Okay.
question from YouTube chat box from our MGM student,
Okay.
Jitendra Malusare. Combination of hydrodynamic cavitation with Fenton's process is more efficient, but
Correct.
there is a formation of Fe sludge, which
Correct.
need to be separated. Sir,
Yes.
he wants you to comment on this.
Yes. So whenever you are using Fenton, definitely you are going to generate sludge. Yes. But it all depends on what is easier for you. Whether it is easier to treat water or not easier, what is important to you? Is it really important to treat water or worry about the sludge which is being generated? So if you look at industry viewpoint, treating water comes very important because then it can be discharged into the outside world. Unless you treat it, the discharge is not going to be possible. Whenever sludge is formed, it can be definitely separated using simple coagulation, simple alum can be used, lime can be used, and that sludge is going to be of much lower proportion, and the industry can safely send it to the hazardous waste management unit. What also needs to be done is you need to optimize whatever ferrous sulfate dosing which you are going to use in the system, and that will also allow you to minimize the quantum of sludge which is going to be generated. So yes, sludge is generated, but it is easier to dispose sludge, and I can optimize the FeSO4 concentration, ferrous sulfate concentration, so that the sludge quantity also can be minimized in the operation.
Okay. Sir, there are a number of questions in the chat box, but I have sorted some of them and you have already clarified in the PPT.
Okay.
There are a number of thanks and nice session and appreciation for your session. All we are good to see you. I will hand over to Mr. Kohli. Hello, sir.
Okay. Thank you, Rajashri. Yeah. Kole, sir.
Yes, sir. So really, it is indeed a privilege to have you as a resource person in this faculty development program. The talk was really informative and insightful, as we can see that how many number of questions are over there. So I'm very much sure that it will help to kindle a renewed enthusiasm in all the participants for their research work, and also I am doubtless that more and more industries must progressively adapt hydrodynamic cavitation technology for wastewater treatment as well as a process intensification of various systems. The talk was really very much beneficial to our all participants. Dear sir, thank you very much for accepting our invitation and delivering such a magnificent speech in this faculty development program of Chemical Engineering Department of MGMCET Navi Mumbai. Once again, we are really grateful to you for making time to speak to participants over here. Thanks a lot, sir.
Okay, thank you. Yeah, thank you, Dr. Kole. So as I said, I think right in the beginning, it was good interaction for me also. Definitely, this doesn't replace the personal interaction, and maybe we could have had some snacks after this particular webinar if it was a organized event in person. So we will definitely do that when we meet maybe next time. I hope the lockdown is over very soon, and then all the personal interactions are going to continue. So thanks very much, and looking forward to meeting you again personally.
Thank
Okay.
you, sir.
Thank you very
Yes,
much.
thank you.
sir.
Thank you, Rajeshri. Thank you all.
Thank you, sir. Thank you. Thank you, sir. Video. Now I would like to announce that the next session will be conducted by Professor Prajakta Angre. Yeah, already the time is over. So, Prajakta madam?
Yes, sir. Are you able to hear me, sir?
Yeah, yes, madam. Dr. Rahul has also
Yes.
connected.
Can we start, sir?
Yes, madam. Yes, we can.
Okay.
Please. Hello.
Yes, sir.
Yes,
A very
madam.
good evening to one and all. Sir, are you able to hear me?
Yeah, definitely.
A very good evening to one and all. So after a very informative and interactive session by Dr. Parag Gupte, sir, I take immense pleasure to welcome our next international guest speaker, Dr. Rahul Bhosle. A very warm welcome, sir. Now let me give a brief introduction about him. So Dr. Rahul Bhosle is currently working as an associate professor at Department of Chemical Engineering, Qatar University, Doha. Dr. Bhosle has received his bachelor's from Mumbai University, master's in chemical engineering from Institute of Technology, Mumbai, PhD in chemical and biochemical engineering from South Dakota Schools of Mines and Technology, USA. He also has 1 year postdoctoral experience from ETH Zurich and Paul Scherrer Institute, Switzerland. The research program led by Dr. Bhosle is focused towards solar thermal processes, materials and catalysis, alternative fuels, energy storage, desalination, CO2 capture and utilization, thermodynamic and kinetic analysis, and wastewater treatment. This research program collaborates with several national and international institutes such as South Dakota Schools of Mines and Technology, USA, University of Florida, Virginia, Commonwealth University, Paul Scherrer Institute, Switzerland, University of Ontario, Institute of Technology, Canada, CRNS, University of Stavanger, Texas A, University of USA, Qatar, and Pandit Deen Dayal Petroleum University, India. Dr. Bhosle has received around 2.23 million US dollar research funds and published 174 research articles with 1,809 citation, 27 H index, and 49 I10 index. He has also contributed to several national and international conferences via more than 150 oral and poster presentation. He currently serves as a guest editor for the journal like Science of Total Environment, International Journal of Hydrogen Energy, International Journal of Energy Research, Environmental Science and Pollution Research, Greenhouse Gases Science and Technology, International Journal of Exergy. Dr. Bhosle served as a conference chair for the 8th GCGW conference, which is organized in Doha, Qatar in 2019. He also contributed as a conference co-chair for the ICA FEE 2019 conference at Taiwan and executed organizing committee member for the 7th GCW conference ICAFFE 2018, China. He's received several awards such as Excellence in Research Award, Mines Medal Fellowship, and multiple best oral and poster contributions. With this excellent academic background, I request Dr. Rahul Bhosle to proceed with his presentation.
Thank you, Ms. Prajakta. Can I share my slides now?
Yes, yes.
Yeah, 1 minute.
Yes. Yes, Dr. Rahul.
So please let me know if you can see the slides and hear my voice
Yeah,
clearly.
yeah.
Yes.
Yes, yes.
First of all, I would like to thank MGM, Department of Chemical Engineering, for inviting me. Also to Prajakta, who considered me to be a part of this talk event, and she actually talked more than expected. So let's start with the topic itself. I'm going to talk about production of solar fuels from water and CO2. This is done by using thermochemical reactions and by using solar energy. This work is done at Qatar University, Doha, in collaboration with several institutes around the world. So let's begin. This slide I will skip because anyway, Ms. Pragit already explained a lot of things, so I will not go into this. But I would like to show you this slide because I know that some of you must be not knowing about Qatar University at all. So let me introduce the place where I work. Qatar University is located in Doha, Qatar, which is around 3.5 hours from Mumbai by flight. This university is established. Sorry, this university is established in 1974. It has around 2,500 undergraduates in different sectors and around 1,000 employees, including faculties. These are some of the pictures of the campus, just to show you how it looks. We have several colleges in the Qatar University, such as College of Engineering, College of Medicine, College of Pharmacy, College of Arts and Sciences, Business and Economics, Law, and others are also there. To be specific, we have around 8 or 9 engineering disciplines in College of Engineering, which includes architectural engineering, chemical engineering, civil engineering, computer engineering, computer science, electrical engineering, mechanical, and industrial system engineering. I belong to the chemical engineering department. Recently, the rank of the university is increased a lot. I mean, in 2016, it was around 500 worldwide rank, but now it's around 250, 245 actually. So it's within the top 250 in the worldwide ranking. When I came here, actually, I thought that maybe the place will be different because I was in Switzerland, and so my impression was different. So maybe you all have the same kind of impression that maybe I'm sitting in the desert and giving the presentation, but that's not the reality. Basically, if you check the pictures below at the bottom, this is Qatar. We have Pearl Qatar, where I live. Then we have Suqwa Cave. We have Qatar National Library, the picture number 3, which is one of the world's largest library. Then we have, this is the skyline for Doha. And in 2022, Qatar is organizing and hosting football FIFA World Cup. So the place is not like what we imagine. The things are different here. So let me start with the actual presentation. This is the first slide, which will help you to understand why I'm doing this research. And also this is the motivation behind my research. In 2010, the population of world was 7 billion and the energy requirement was 15 terawatt. And it is expected that by 2050, the population will go up to 10 billion and the energy requirement will increase up to 30 terawatt. Currently, we are using all these 6 sources, which is in the picture actually, which helps us to generate the amount of energy which we require, which is 17, 18 terawatt at this moment. And mainly it is come from oil, gas, and coal, which is fossil fuels, around 87% of the energy. 13% of the energy we are getting from other sources such as hydroelectric, nuclear, or alternative. But we all know that the oil, gas, and coal are limited, and the continuous use of oil, gas, and coal results into release of CO2, which is considered as one of the major greenhouse gases. As you can see, the CO2 concentration increased from 325 ppm in 1970 to 525 ppm to 2050. So, I mean, not only the sources are limited, but we are having some environmental issues because of this continuous use of oil and gas. So that's why this actually, you can say, focused me towards producing solar fuels. based on my PhD experience and postdoc experience, I formulated a research program in which we are trying to eliminate the use of fossil fuels for the production of liquid transportation fuels. What we are doing is we are trying to use the water and the CO2 as the feedstock for the production of either hydrogen, which can be used as fuel directly, or syngas, which can be then converted into the liquid transportation fuels. Well, use of hydrogen is possible, but in our day-to-day life, we need a different engine to run the hydrogen because it's a gaseous fuel. But if we produce syngas instead of hydrogen, that will end up in producing liquid transportation fuels. So the car will be the same car, but only the fuel which we are getting, like gasoline or diesel, which will not come from the fossil fuel, it will come from water and CO2. So this is the overall picture. Now, another question must have come in your mind that what will be the source for the water and CO2? Now, CO2 will come from the industry. We are actually trying to capture the CO2 from the atmosphere. We are working on that as one of the projects, but it's not that easy. It takes time. It will take time actually, and hopefully we'll be able to get it enough CO2 from the atmosphere so we can run this process. But currently the plan is to use the CO2 coming out from the industry. And the second thing is the water. Well, we need pure water, but what we are doing is we are not using the water which we are drinking now. We are desalinating the water. We have a solar desalination plant in our lab, which is also one of the projects which we are working on. And we are using that water coming out of the desalination plant as the feedstock. So basically, overall, if you see, we are getting CO2 from industry, which is anyway we are emitting to the environment, and water from the seawater. So basically, the source is also, we are not going to get affected because of the sources. You can see some solar towers at the top of this slide. The reason for this is this process is highly energy intensive. For example, I will explain you on the next slide what is the reaction chemistry behind the process. But the first step of the process requires a high temperature. It's a high temperature process. So instead of using the electricity or any other source, we decided to run it by using the solar thermal energy. So that's why this is called as a solar fuel. We are using solar thermal energy to run our reactions, thermochemical reactions for the production of solar fuels. So this is the overall picture which we have, the motivation behind the research. Now the second slide is more about the chemistry. Here you can see a very highlighted word is MO in the left hand side. This MO is called as metal oxide. Now, actually, it takes part in the reaction, but basically the properties the metal oxide has is kind of a catalyst or a semi-catalyst, you can say. What happened in the first step? In the first step, where we have the where we can you please stop to mute all? Actually, I'm able to hear others' voice. Okay. So then the first step, which is a thermal reduction step, in which we use solar thermal energy to reduce the metal oxide. Reduce means we are taking the oxygen away from the metal oxide. So the reduced metal oxide, actually will be reacted with water and CO2 to produce syngas. If you use steam, then it will only go for the hydrogen. So this is the overall reaction chemistry actually. Basically, as I said, the metal oxide is not used in the process. It is recycled and it was used multiple times. We can do that. So it can behave as a semi-catalytic material. So overall reaction chemistry will be like metal oxide driven by solar thermal energy. So it becomes reduced metal oxide, and the reduced metal oxide will be reacted with water and CO2 to produce syngas. The net reaction, because metal oxide is not used, so we can say that the solar thermal energy will split the water and CO2 to make the syngas or hydrogen. Now, all the processes, all the technologies we work, some are advantages, some advantages are there, some limitations are there. This process is advantageous because we can actually use solar energy to produce the fuels. And also the metal oxide is not used. So basically we can regenerate and we can reutilize the same metal oxide, which will actually reduce the cost. And the next thing is we are producing the hydrogen and oxygen in separate steps. So separation will not be an issue. But limitations are there. For example, as I said, the first step is high temperature step, high amount of energy is needed. So that's why that's one of the limitations. What we are trying to do is we are trying to reduce the temperature by doing some materialistic approach. I will explain you that later. And the other thing is that we want actually to improve the fuel production capacity, so that anyway, basically we will be able to produce the fuel at a lower cost. So let's go further in the topic. Metal oxide redox materials. Actually, there are two types of metal oxides. Uh, all the research groups are investigating. First is the volatile metal oxide, which includes zinc oxide and tin oxide, and the other one is non-volatile metal oxide. Let me explain you what is volatile and what is non-volatile first. Volatile metal oxide means that when we heat it in the thermal reduction reactor, its phase changes. So it goes from solid to gas, and then the recovery of the metal oxide after reduction is very difficult. So that's why other groups are working on non-volatile metal oxides. For example, my group, we are working on ferrites, doped ceria, and perovskites. The advantage with these metal oxides are they remain in the solid or the solid solution phase. So they doesn't go in the gas phase. So the special amount of quenching or special kind of reactor arrangement is not needed in this case. So now hereafter, whatever I will talk about, I'll talk about the ferrites, doped ceria, and perovskites. Can anyone confirm if they can hear my voice clearly? Because I see some messages that my voice is low. Everything is okay?
It is clear.
Okay, fine.
Yes, sir, it's clear.
Okay, so basically the blue box I'm showing you here, it's actually the same thing which I showed in the previous slide. The first step is the high temperature first step where I use the solar energy, and the second step is a low temperature exothermic reaction step where I don't use the solar energy and I produce the syngas. This is what we are doing currently in our lab. We are producing solar fuels, and it has 6 different approaches. I mean, 6 different aspects of the research. First one is the metal oxide synthesis. Here, actually, we are synthesizing the metal oxide by different methods. We are not purchasing any metal oxide from any company because we are playing with the chemistry. We are trying to develop different kinds of metal oxides in our lab. We are using different methods actually for that. After synthesizing and characterizing, we are testing the metal oxides in the lab scale experiment, which is the second circle you can see. Here we have two reactors, two reactor arrangements we have. One is the high temperature thermogravimetric analyzer, and the second one is a packed bed reactor where we are testing the materials. Then we are doing the kinetics and economics analysis. We are not doing that much in that area, but we just started. The number 4 is solar reactor efficiency analysis, which is our expertise. What we are doing is we split this part into 2. In the first part, we are from the literature, we are generating the thermodynamic data, and we are utilizing that data to see how much solar energy is required for the reactor and other process arrangements, and also the solar reactor efficiency of the process. Each metal oxide has a different efficiency. And the second part, what we are doing is instead of doing the theoretical work, we are actually utilizing our own experimental data to model actually the reactor arrangement, and then we are trying to find out the efficiency of the process. The number 5 and number 6, we don't have the complete facility here in Qatar, so we are collaborating with Switzerland, with USA universities for the solar reactor design and development and pilot scale solar experiments. I will show you at the end of the presentation what we are actually trying to do. So today I'm going to talk mainly about the first 2 boxes, the metal oxide synthesis and the laboratory scale experiments, because that's the initial step. And the materials which we are identifying from this step, we are taking to the next level for the solar reactor design and solar reactor experiments. So let's start with first with ferrite materials. Let me explain you what is ferrite material. Ferrite means we know iron oxide. We dope the iron oxide with different metal cations. For example, we dope iron oxide with nickel, so it becomes nickel ferrite. If you dope ferrite with cobalt, it becomes cobalt ferrite. So this is called ferrite materials. This slide will tell you that ferrites have been used previously by other investigators, including me, for thermochemical splitting of water for the production of hydrogen. You can see nickel ferrite, cobalt ferrite, zinc ferrite, manganese ferrite, nickel manganese ferrite. So several combinations have been used. And these are the temperatures and the regeneration temperatures we have employed. If you check the numbers on the last column, which is the hydrogen yield, the nickel ferrite and cobalt ferrite seems to be more advantageous towards production of solar fuels, basically solar hydrogen, than the other metal oxides or the ferrites we have used. So what we have decided that why not we test, because this is done only for the hydrogen production, but for the production of syngas, we need carbon monoxide also. So we decided to test the nickel ferrite and cobalt ferrite materials for the solar thermochemical CO2 splitting, from which we get the CO. So the first step we did is synthesis of the ferrites. We use sol gel method. If you need some information, you can check the paper. I gave you the link below. Sol gel method is helpful for producing nanocrystals. So what we did, we used the cobalt. This is example of cobalt ferrite. We used the cobalt nitrate precursor and iron nitrate precursor. We mixed that in ethanol. The precursor solution is generated. In that, we added the oxygen scavenger. In our case, we use propylene oxide to the precursor. One second. Yeah. Then the gel formation is achieved. After the gel formation, the gel was aged and then dried. And after that, it was calcined, or you can say annealed. Calcined means we are heating the powder which we get after the gel breaking up to 1000 degrees Celsius or more than that, so that it will get cooked nicely and the combinations will happen, so that at the end we get the cobalt ferrite nanocrystals. So this is the sol gel method. This is one of the methods we are using. I will show you later what other methods we can use to develop different materials. Then after synthesizing, the next step we did is characterization of ferrites. We use X-ray diffraction to find out the phase composition. We used BET surface area analyzer to find out the surface area and the porosity of the material. We use the scanning electron microscope for find out the material morphology, and also the TEM will help us to find out if we are able to generate the nanomaterials or not. So let's see the results. The first one is the XRD of ferrites. Now you can see two sets here. One is the nickel ferrite set and the other one is the cobalt ferrite set. You can see, for example, in nickel ferrite, we have nickel 0.2, 0.4, 0.5, 0.6, 0.8. So we actually played with the chemistry. We put 20% nickel in the iron oxide, then 40% nickel, 50% nickel, 60% nickel. So what we're doing here, we are actually replacing the iron part, which is less reducible, or you can say less active, with the nickel part, which is more active. So we are making this. So we synthesize 6 nickel ferrite, different morphologies and different crystal structures. And similarly, we have the cobalt ferrite. So the XRD tells us that yes, whatever we have planned, we have synthesized successfully. In addition to XRD, we did the EDS analysis also, which help us to further confirm the elements involved and what are the percentages. So these are the nickel ferrite, cobalt ferrite we have synthesized. After that, we also did the BET surface area analysis, and because it was calcined at 1000 degrees Celsius, the surface area was around 10 to 15 meters square per gram. After that, we did the SEM and TM analysis. These are the sample images. Actually, all the images looks like this. So I just put the sample images for selected nickel ferrite and cobalt ferrite materials. The SEM images on the left-hand side, AA, and the TM images on the right-hand side, BB. So if you check the bar, which is 20 nanometer in the first picture and 50 nanometer in the second picture, you can clearly see that we successfully synthesized the nanoparticles of nickel ferrite and cobalt ferrite. So after doing this, the material is done now. We synthesized nickel ferrite, cobalt ferrite as we wanted. Now the next step is to test them. To test them, we have a high temperature TGA DAC setup in our lab. The left-hand side is the picture of the TGA setup, the actual picture, and the right-hand side is the schematic diagram. So you will see what is inside. We have the alumina tube, we have the sample chamber, we have the temperature control thermocouple, balances at the top, the gas flow coming in, cooling water is coming in. So basically, this is the entire basic thing of this TGA setup. What we did this TGA setup and we connected to our entire reactor arrangement. For example, we have the gas supply coming, protective argon gas is used, which avoid the graphite furnace to get bad, to worse. We use argon carrier gas as the inert gas, like a sweep gas, you can say, during the reduction step. And then we use the CO2 50%, argon 50% gas during the oxidation step. This TGA setup is connected to gas analyzers. So whatever gases coming out from the setup went to the gas analyzers. And in addition to the weight change, we also found out how much is CO produced and hydrogen produced, for example, in steam generation or steam splitting by using the gas analyzers. Before I show you the actual results, let me explain you how the TGA works and how the system works, TGA system. So basically in this picture, you can see that the left-hand side is the temperature from 0 to 1600 degrees Celsius. And the right-hand side is the mass change. So initially the mass is 100% because we put like, okay, one more thing which I want to share, that this TGA has a limitation that we cannot go more than 150 or 200 milligram of sample mass. So actually we put like 75 to 100 milligrams of sample mass for our each experiment. What happened here, that if you check, once you heat the temperature up to 49 degrees Celsius, the weight decreases. The weight decreases because the oxygen comes out. And when we reduce the temperature here, which is 1000 degrees Celsius, we switch the gases. We switch the gases from argon to CO2. So because of the CO2, the oxygen will take, the material will take the oxygen again from the CO2 and the weight will be increased. So decrease in the weight means the material is reduced, the oxygen comes out. And increase in the weight means the oxygen is picked up by the material and the CO2 will be split into CO and O2, and water can be, steam can be split into hydrogen and oxygen. And again, we are having the gas analyzer at the outlet, so we can check the gases. So this way we did multiple cycles. Actually, I mean, we use the same metal oxide for multiple times because, as I said, the metal oxide has the property with the help of which we can use the same catalyst or same metal oxide for multiple cycles. So this is a picture which shows that we have some sample TGA plots for NF6, NIF8, and NIF10. So based on the TGA results and the gas analysis which we did, we converted the data into micromoles per gram of fuel produced. So this table is for nickel ferrite. You have, as I told you, we have 6 different metal oxides, nickel ferrites synthesized. So this actually we did 3 cycles, cycle 1, cycle 2, cycle 3. And if you can check, if you can compare the ferrites together, the last one, which is NIF10, seems to be the more beneficial ferrite in terms of the fuel production capacity. It has the highest O2 release and it has the highest CO production at these conditions: thermal reduction at 49 degrees Celsius for 60 minutes and CO2 splitting at 1000 degrees Celsius for 30 minutes. Similar to the nickel ferrite, we tested the cobalt ferrite materials, and again we observed that COF10, which is the last one, has the highest amount of fuel production capacity at the same experimental conditions. So until now, we realized that out of the 6 nickel ferrites and 6 cobalt ferrites we have synthesized, the NiFe2O4, which is NiF10, and COFe2O4, which is COF10, are the best samples. But we have done only 3 cycles. What actually the solar thermochemical community wants, that we want to run for 1,000, 10,000 cycles. I mean, that is the aim, but it's not possible in the lab to do 10,000 cycles. Otherwise, we will end doing the same research for 10 years. So that's why what we did, we decided to use the same materials and did at least 10 cycles in case of nickel ferrite materials and in case of cobalt ferrite materials. So this slide tells you about the nickel ferrite materials. If you check again, I gave you all the information here. Average amount of O2 produced per cycle per gram, and average amount of CO produced per cycle per gram. So if you check the nickel ferrite, which is at the end, is the highest. That's why I put that in the red, and others are in blue because they are not that highest as compared to NiFe2O4. In terms of O2 release and in terms of CO produced. So basically, it indicates that out of the 6 nickel ferrites we have synthesized, NiFe2O4 is capable of producing the highest. Similar thing was observed in case of cobalt ferrite, that COFe2O4 is capable of producing the highest. Now, if I compare cobalt ferrite with nickel ferrite, they're almost identical, only slight difference is there, maybe because of experimental error, or maybe the cobalt ferrite is slightly better than nickel ferrite. So this is what we have observed in this case. So after doing this, one more thing which came in our mind, that why don't we check the phase stability, because we are doing multiple cycles, so we are not sure. We assume that the cobalt ferrite crystal structure remains the same, but we should check actually what happens. So what we did, we checked the phase stability of the nickel ferrite and cobalt ferrite also. So in this picture, you can see the different XRD plots. The first one, which is at the bottom, is the as prepared, the same plot which I showed at the start of the presentation in the nickel ferrite. Then we took the sample away after 5 cycles, 10 cycles, and 20 cycles, and we did the XRD to compare. And if you check the peaks, all the peaks are similar. We also did the EDS analysis to confirm. And this indicates that the nickel ferrite crystal structure remains intact. It doesn't go in any other crystal structure, or it's not broken like nickel and iron oxide. So we can say that whatever amount of fuel we have seen in the previous slide is because of the NiFe2O4 crystal structure. Similar thing was recorded in case of cobalt ferrite. Like, it also remains quite stable. And we can claim that whatever fuel production we have seen is because of the COF10. After doing this is what we have done until in case of ferrites. Then we move towards, let's say, dope ceria. Now, in case of ceria, what happens? Ceria is a crystal structure of CeO2. So what we will do in ceria, we'll again do the same thing. We will try to dope the ceria crystal structure with different metal cations, from transition metal, from lanthanides, from alkali and alkaline earth metals in all these cases. It is expected that the doping of these metal cations in the ceria crystal structure actually reduces the partial molar enthalpy, which helps to reduce the material faster and at a lower temperature. So what we did 3 actual different studies. The first study, in which we doped the ceria material by transition metal cations like nickel, zinc, manganese, iron, copper, chromium, zirconium. You can see this. Here we use co-precipitation of hydroxide method. Why? Because in the previous investigations, people have used the same method. So just to compare with the other people, we did this, that okay, co-precipitation of hydroxide is used. This is the picture. If you need more information, you can check the paper, which is given below. Again, the same thing is done, that we did the XRD check and also the EDS check to find out if we synthesize the same material or not. And the right-hand side picture, this is actually the TJ plots of each material, the 10 TJ plots. The experiments were done continuously. Around 22 hours of experiments are done. And this TJ plot was used to find out the actual amount of CO and O2 production capacity of each ceria material. These are the numbers. Now here I put the ceria in black, because we are comparing what will happen when we dope the ceria with the transition metal cations. So ceria is in black. The red color means that dopant actually improve the O2 production capacity or CO production capacity, and blue means it doesn't have much effect. So if you check on the first part, which is the O2 production capacity, the thermal reduction capacity, zinc, iron, and chromium actually help to improve the O2 release capacity of ceria, and nickel, manganese, copper, cobalt, and zirconium are not that beneficial. On the other hand side, if you go to the CO production capacity, only zinc and iron are capable of helping ceria to produce more CO as compared to actual ceria, and other metal oxides are producing lower amount of CO. So from this study, we identified that zinc, iron, and chromium are suitable actually for the next study. So instead of testing all the materials again, we can focus on zinc, iron, and chromium only. The second study we did is we doped with lanthanides. Lanthanides means we have lanthanum, praseodymium, samarium, neodymium, gadolinium, terbium, and other lanthanides actually we have. Same approach was applied. We use the co-precipitation of hydroxide method, so we can compare our own materials together. XRD is done. Again, these are the TJ plots for all the materials. Now, here the things are quite interesting. If you check the O2 production capacity, almost like 5 out of 8, 5 dopants are successfully helped ceria to improve the O2 production capacity. For example, lanthanum, samarium, terbium, dysprosium, erbium actually helps to improve the thermal reduction capacity of ceria. But when it comes to the CO production capacity, only lanthanum is beneficial. So based on this study, we found out that if we want to improve the O2 production capacity, we have 5 options from lanthanides. But if we want to improve the CO production capacity, we have only 1 option from lanthanide, which is helpful. The third one, which we did, is the remaining, for example, lithium, magnesium, calcium, strontium, barium, and tin from different sections. Here again, the same approach was applied because we want to compare them together. The thermal reduction was carried out at 14 degrees Celsius and the splitting was carried out at 1000 degrees Celsius. Here, the things are more interesting because all the dopants are successfully helped Syria to improve both the thermal reduction capacity and the CO production capacity. Especially if you check the tin has the highest amount of O2 released and CO produced as compared to all the dopants we have used until now, transition, lanthanide, and this. So based on this, we identified that now we are taking this to the next level to find out which materials will behave better in the pilot scale reactor, which I will show later actually. So this is the initial study we did for the Syria. Similarly, for the perovskite material, what we have done is perovskite is recently explored actually in this ASA research, around like 7 to 8 years. Before that, only the Syria and the ferrites and others were used. So perovskites were used, and what we did is we decided to do the perovskite analysis by doping as much or preparing as much perovskite as we can. So we did La-based perovskite, LaSrMnO3, NdSrMnO3, samarium SrMnO3. Actually, these dopants are selected based on their ability, their theoretical ability also, and also previous analysis. Here we use a different method, solution combustion synthesis approach. I would like to clarify a few things that we can develop all these materials by all the methods, but I'm specifying specific method here because we are using this method because the others have used, so we can compare with that. I mean, if you use other method, then people can claim that you use a different method, so we cannot compare. So we have to compare apples with apples, not apples with bananas. That's the thing. So we did the solution combustion synthesis approach. Here, actually, we developed around 8 different perovskites. Now, solution combustion synthesis approach has the advantage that it can produce highly porous materials. So if you check the SEM analysis, you can check very highly porous materials are there. And again, we did the TG analysis as we did for others, same temperature, same conditions, because we want to compare together at the end. Now here, what I didn't put anything black here because all the materials are standalone. There is no base material with which we are comparing. But I put a red color here because that is the most highly efficient material we have. For example, PrSrMnO3, which produces 144.8 micromoles of O2 and 252.3 micromoles of CO as compared to others. Also, if you compare all these materials with previous studies, which I have seen, you will notice that the perovskites are more beneficial than Syria and ferrite. That's why recently the solar thermochemical community is focusing towards perovskite. But what we thought that instead of focusing on any random perovskite, which actually others are doing, we decided to do this study and find out the best possible perovskite and then focus on only one perovskite, which we can take it to the next level. So we found out that PrSrMnO3 is the best in this list. But if you check the composition, we put a fixed composition. For example, La.5, Sr.5 MnO3, Pr.5, Sr.5. So 50% praseodymium, 50% strontium was there. But we can play with this chemistry. We can do 10% praseodymium, 90% strontium, 20% Pr, 80% Sr. And we did that actually. In our next study, we studied on the PrSrMn actually. Basically what we did, we actually played with the X here. We move the concentration of Pr from 0.1 to 0.9. And similarly, the strontium concentration was moved from 0.9 to 0.1. This is the material chemistry approach actually. So we develop around 9 PSM perovskites to find out which one is the best, because in the previous study, we found out that Pr.5, Sr.5 was the best, but we don't know if 0.1 and 0.8 has a different role to play. So when we compare, you can see here, we found out that in terms of thermal reduction capacity, Pr.3, Sr.7 is more beneficial, because if you check the numbers, it is the highest amount of O2 produced. This material can produce highest amount of O2. And in case of the CO production capacity, the Pr.2, Sr.8 is the highly efficient. in terms of the CO production capacity. Even PR.3, PSR.7 is almost like number 2 actually in this case. So from this study, we can conclude that PR.2 and PR.3 are the two beneficial composition which we have, which we can further explore. We can do maybe 1,000. Actually, we are doing. I didn't put this here in this slides. We have done around 1,000 cycles in ferrites and 1,000 cycles in Syria selected, not in perovskites yet. We are working on that to see how the perovskite will behave for 1,000 cycles. Now, actually, after doing this, as I told you, that the TJ has a limitation. We cannot go more than 200 milligrams. But actually, when we take this system to the pilot scale, we need to go into grams and kilograms. So we developed a packed bed reactor setup in our lab, which capacity can go up to around 5 grams. So we are now testing our materials for both steam splitting and CO2 splitting, all the best materials which we have identified until now. In addition to that, the results which we are getting from these experiments, we are trying to model them to find out the kinetic expressions and the efficiency analysis. One thing you must have observed that I have not shown you any solar energy utilization anywhere. This is all lab scale thing which we are doing. But as I said, we have to do solar experiments, and solar should be there if we say it's solar fuels. We are now working on solar reactors. Now, these are the pictures from different publications, and we are actually connected with all these collaborators now. Different arrangements are possible in solar reactors. For example, this is a cavity-based reactor, the first one. Then we have the membrane reactor. This is actual solar lab scale thing. For example, this is a solar reactor, the cylindrical part. And then we have the high flex solar simulator. So this is quite expensive, but this helps actually for you to actually do the actual solar experiments in the lab instead of going outside and do it like that. So we are working on this. We are we are collaborating with different institutions. What we are doing is that the material aspect is done by us. We are trying to find out the best possible materials. And then the other group is actually, because they have the expertise in reactor design, mechanical engineering people are there. So they actually combine with us like chemical engineering aspect, material aspect, and the heat transfer, mass transfer aspect. And we are trying to develop the best possible reactor arrangement. This slide actually shows you how we are going to do the actual solar experiment. Actually, I would like to tell you that these pictures are taken by me because I was a part of a team which went to France and did the actual solar experiments in my postdoc. So basically what we did actually, this is actually on the right hand side, if you check like a cylindrical thing, this is a solar reactor. The capacity is 100 kilowatt. 100 kilowatt means that much amount of solar energy it can take, that amount of heat it can take. The reactor is heated by using the actual solar energy. So basically the panels gives the solar energy to this concave shaped solar furnace. And this building here, actually we place the solar reactor. So all the energy goes inside through this cavity, and the cavity is heated. So we are not using any electrical thing, any nuclear thing, nothing. We are just clearly using the solar thermal energy to drive the reactions. And similarly, we are actually trying to, this is done for actually zinc oxide, and we are trying to do it for Syria and ferrites. We are collaborating. For example, this slide will help you to understand what we are doing. We are collaborating with India, with USA, 3 universities, with Canada, with Switzerland, and other who are actually potential candidates who can do the solar experiments, who can do the solar reactor design, and all these things. So basically, this is what I have. Maybe my presentation was short, but I don't want to bore you guys. I just wanted to give what is important, what is easy for you to understand. So thank you very much again for the MGM Department of Chemical Engineering, for the faculties to invite me. This is my information. If you want to contact me anytime, you can email me. You can call me also if you wish. If you want to check my papers, I put the Google Scholar link here. If you want to read any paper, if you don't have any access, just let me know. I will give you the paper also. And this is what I have for today. I again would like to thank Dr. Kole and Ms. Pratita Angre for inviting me and considering me potential enough to help others to know more about the solar fuel production. Thank you very much.
Thank you, Rahul sir. This is Dr. Rajashri. We'll wait for a minute for questions.
Can I stop sharing the slide?
Yeah, sure. Dear participants, you are requested to post your questions in the chat box. Sir, your session was very informative and we are receiving lot of thanks in the chat box and lot of appreciation. Professor Karpe wants to say, sir, it is really it's a innovative work you are doing in chemical engineering world.
Thank you very much. Thank you.
There is a question from Mr. Praveen Tadkar. Can you explain about solar tower?
Solar tower is something like basically it's like a tower. We have a reactor arrangement set up at the top, and the solar panels will transfer all the energy based on the direction of the solar panels to the up. It's called a tower because it's like a tower. I mean, it's just have a design of a tower. So basically, it's like a place where we can keep the solar reactors. That's it.
Okay. There is one more question. Mr. Ajit Kumar Gudekar. Sir, are you in touch with NISE India for any possible technology development?
Well, not yet.
Okay. Mr. Milind Surve wants to ask, can we use simulation models to predict the efficiency of metal ferrites after say 10,000 cycles?
Yes, actually, look, I would like to explain something. What we are trying to find out that we are trying to find out a metal oxide which can produce the same amount of oxygen and CO in multiple cycles. So even if you do 10,000 cycle, 1,000 cycle, 500 cycle, the average amount of O2 produced and CO produced will remain the same. So yes, with the help of simulation models and if you have the thermodynamic data, yes, you can do that. We are doing that. If you want, I can share some papers to you also. Yes, you can do that. We can find out the efficiency of the process.
Hello. Hello.
Yes.
Yeah, can I ask question?
Yes, please.
Is there any group who is working on modeling and simulation of these photo reduction reactors?
You're talking about my group?
Yeah, I mean in your university.
No, we are not actually working on photo reduction reactor. We are actually we are working on thermochemical reactions, experimental plus the modeling part, not the photo reduction reactions.
Okay, so thermochemical reactions.
Thermochemical reactions, solar thermal energy, yes.
Okay. So you are not using UV energy. You are using only thermal energy from the solar.
Yeah, we are actually using the whole spectrum of the solar. We are not going focus on any filters because we need a high temperature. For photo, you need to have specific kind of solar radiations. Here, you can use all.
Okay, sir. Actually, I am a professor in an engineering college, and I am working in ICT on my PhD for modeling and simulation of photocatalytic reactor. So, in case if I get any queries or I want to ask you some questions, I'll definitely take your email address and will correspond with you. Is that fine with you?
Sure, no problem.
Okay, thank you very much.
Thank you, ma'am. Dear participants, please post your questions in the chat box to take up it quickly. Sir, the next question is related to chemical solar lamp. Yes, that was the question. Is there any innovation related to chemical solar lamp?
Well, I cannot comment on that because I am not expert in that field. But what I can tell you that we are producing fuels. Basically, we are not dealing with the chemical solar lamp or something like that. We are just focusing on transportation fuel part. So if I answer something that might be wrong thing, so I will not comment anything on that because we are not working on that part.
Okay. Sir, the another question from Mr. Ganesh Shinde. In spite of huge potential, why harnessing of solar energy is less in India? Any comment on this?
Let me tell you honestly. For example, I just show you the solar furnace. It was 1 megawatt solar furnace, which is in France. To develop that solar furnace, you need a lot of money. It's not that easy. So basically, we don't have that much amount of funding, or the government doesn't want to fund that area. Maybe that's why we are not. And if we want to do this, we have to take it to the Rajasthan area or some area because that's the where we can do this. So maybe that focus is not there. As far as I know, all the people who are working on this area are either from US, Australia, Europe, and now I am from Middle East. So actually, the Indian part is lagging in this side. So that's why maybe the funding issue is also one more important factor in this case.
Okay. Mr. Ajit Kumar Gudekar wants to ask, what time frame you see for the solar fuel to be a reality?
It will take time because we are just now exploring the materials. We are still working on the solar reactors. As I showed you, the 100 kilowatt solar reactor, that was, I think, one of the examples of we are taking it to the pilot scale. Other than that, we have very few examples. So we are still working. We are at the initial stage. But if it will be successful in future, of course, we will have a different kind of thing because we are trying to completely eliminate the fossil fuels. So that will help us. But at this moment, we need time. Yeah.
Okay. Sir, Mr. Bhagat, Sanjay Bhagat has made a statement and he needs your comments on that.
Okay.
Sir, in coming days, chemical engineering labs will run on solar energy.
What kind of comment he wants from me? Well, to run the
what-
chemical engineering labs on the solar energy, the first thing is that you have to produce the electricity by using solar. If you can achieve that, yes, you can run the labs because you cannot put solar panels on in each equipment. Each equipment is different.
Yes. There is a question from Mr. Yuvraj Chauhan. What are the applications of solar fuels?
Well, as I explained, we are producing syngas, and as you know that when we break the fossil fuels, also we produce syngas, and the syngas goes to Fischer-Tropsch. So you can produce gasoline, diesel. So solar fuels are basically is the same fuel which we are using now, but produced in a different way, not a conventional way. We are producing by using solar energy. So the system will not change. System will be the same. The only thing is we are trying to avoid the use of fossil fuels.
Okay. Sir, there are many thank you and appreciation and innovative session comments on the chat box. Sir, we are nice to have with you, I guess.
Yeah,
Okay, there is one more. Mr. Sajay Amle.
I
Sir,
saw that. See what
sir, are you using seawater as it is?
we are trying to use, but no, some pre-treatment is required actually. But the plan is that we are not using seawater in our solar reactors at this moment. We have a desalination plant before that. So we are trying to clean the seawater through desalination and then use that water as a steam inside our reactors. Because if I use seawater, then things will be different.
Okay. Prajakta ma'am?
Yes.
Over to you.
Hello.
Hello, yes.
Thank you very much, Dr. Rahul. A very wonderful presentation, I must say. The PPTs are very clear and very descriptive themselves. So very wonderful session. Thank you very much for accepting our invitation. And definitely your work is new and that will be encouraging and motivating many of us to work on that area. So thank you very much.
I
Hello?
would like to add a statement if you allow me.
Yes.
Yeah. Actually, I would like to tell you one thing that I am also from the same part where all these faculties and people are sitting now. I didn't mention the college where I'm from, but basically I'm from KAS and then Patil Engineering College from Pune. So I started there. Prajakta was my actually batchmate, and Dr. Kole was my batchmate when I was at ICT. So things I would like to tell you that
Yes.
we are started at the same level. I am very happy today to explain my thoughts and to explain my research to the same community and the same people from where I am. So I thank MGM community and I thank Dr. Kole and Ms. Prajakta for inviting me for this talk.
Dear
Kole sir?
doctor,
Yeah. Kole sir.
yes, madam. Yes, yes. Dear Dr. Rahul, really I'm very much glad to hear you after, I think, 2008, after
Yes.
completion of your MChem engineer from ICT. So, yes, really, the session was very interesting and insightful. We can see that the participants could not had patience and they directly wanted to have a dialogue with you. So really, it was really wonderful session and presentation. And I will say it is a blessing in disguise that because of having this COVID problem, we can have you right now for this particular FDP. So really very much happy and thankful to you for having with us today for this particular FDP.
Thank you, Dr. Gal. Thank you very much.
Very much. Thank you.
Yeah.
Prajakta madam.
Hello. Now, thank you very much all participants. So tomorrow also we will have two sessions, two eminent speakers from academic background as well as industrial background. From academic background, Dr. Sanjay Mahjani sir, Professor IIT, IIT Powai, and from industrial background, Dr. Sunil Waje. So stay with us tomorrow. Stay safe, stay home, take care. Good day.